Assalamualaikum and good day to everyone. My name is Syaridatul Irma binti Ismail. I'm a postgraduate student in University Putra Malaysia under supervision of Associate Prof. Dr. Amin Syahir Amin Hamzah. So this is my project title, Design of Tripeptide Heteroligand System as Capturing Agent for Mercury Plasmonis Detection. So I will start with general background of my study, which is heavy metal production. Heavy metal are generally referred to the naturally occurring element that can be found on Earth. They are persistent, which can be stored for a long period of time in our environment. Metal ions are required only by certain limit of daily intake, and our body will consume this metal ion through food change and also water intake. They will accumulate in our human organs such as lung, kidney, and liver. So it will result in acute or chronic poisoning and even cancer. So this is the example of metal ion and its source. So my study will focus on the mercury, as mercury is the most hazardous metal ion in our environment. So detecting metal ion is a crucial task right now. So the next is development of biosensor. Biosensor being developed to detect metal ion faster than conventional method. So what is biosensor? It is an analytical device which comprises of biological recognition element that give an output of measurable signal to an interface transducer. So why we use biosensor? Simple, rapid, and also selective. So biorecognition typically relies on enzyme, host cell, antibody, or nucleic acid that could react selectively with the target analyte. So this is the example of biosensor, pregnancy test kit, blood glucose level kit, and also urinate stain. So this is the list of conventional method, which is atomic absorption, microwave plasma atomic emission spectroscopy, inductively coupled plasma mass spectrometry. So the advantages of this conventional method is wide detection range, high selectivity and sensitivity. However, these conventional methods are not suitable for in situ treatment because they are bulky, inconvenient, costly, and also non-portable, and also require high-skilled operator. For example, if we want to test the mercury ion at the river, we have to collect the water sample and go to the lab and do all the process. So it will take some time to get the result. So in this biosensor are widely being used by our researcher, which is by using gold nanoparticle, which is a biosensor colorimetry. So why they use gold nanoparticle? Because this is as you can see in figure 4, the potential application of gold nanoparticle in biology and medicine, where gold nanoparticle widely been used for shape recognition, fluorescent imaging, drug carrier, linker, antigen binding, and also gene delivery. So the properties of gold nanoparticle are high surface to volume ratio, surface plasma resonance, facile synthesis, and also stable in nature. So the color of solution can be changed from red to blue when the gold nanoparticle aggregate in the presence of heavy metal, which is our target molecule. So the focus of my study is designing tripeptide functionalized gold nanoparticle. So as you can see here, in the absence of mercury, which is target molecule, the gold nanoparticles are in monodisperse condition where they are far from each other. No interaction happen. So we introduce the tripeptide that can change the stability of gold nanoparticle and avoid aggregations. So to maintain the stability, after we introduce the mercury, you can see here that the particles are aggregate, which means they're able to detect our detection. So these phenomena are called localized surface plasma resonance. So localized surface plasma resonance has emerged as a leader among laboratory biosensing technique due to its sensitivity, robust, and also simple detection. So as the two nanoparticles getting close, the near field of individual particles will interact and generate a light scattering spectrum that being significantly influenced by the interparticle distance. So in our study, we designed tripeptide that consists of 3 amino acids, which the free amino and carboxyl group are potentially used for sensing metal ion. So this is the first part where we designed the tripeptide. So designing ligand relies on the selection of amino acid that can be conjugated on nanoparticle. So while we're designing, as you can see in our tripeptide, we have cysteine in the middle, as cysteine got tire group which can conjugate it onto the surface of the nanoparticle, and first amino acid entered. So for our first tripeptide, we place the aspartic acid as first amino acid and histidine. This one follow the accumulative feature where histidine at the third place. So for our second tripeptide, we try to positioning the histidine at the first place and aspartic acid at the third place. So this is the characteristics of tripeptide, which is consists of polar, acidic, and basic amino acid. So the next part is characterization of tripeptide. For characterization, we want to see the colloidal stability and structure of tripeptide upon conjugation of core nanoparticles. So we are studying using V-Vir spectra and also the S. So as you can see from the figure, there is no peak shifting or shoulder peak, which indicate that good nanoparticles are stable upon the tripeptide are stable upon conjugation onto the gold nanoparticle surface. So we also done particle size, PDI, and zeta potential for the tripeptide, and you can see here that no very slightly difference between bare nanoparticle and also the tripeptide nanoparticle. And from the PDI value also we can see that the particle are monodispersed and also no aggregation occur. So this is the negatively charged of our tripeptide. So we design our tripeptide to have negatively charged as we want to capture mercury that bear positively charged. The next part is optimization, where we optimize the concentration and pH to stabilize and also to enhance the sensing signal. So we calculate the absorbance ratio and choose which concentration and pH are suitable for our biosensor, our capturing agent. So for HCD, as you can see, A is HCD. We can see here that concentration 0.2 millimolar and also pH 11 are the most suitable as they give out the highest sensing signal. However, for DCH AUMP, you can see here that 0.10 millimolar pH 9 give the highest sensing signal. So we will proceed with this concentration and pH for our next analysis. So in our study, we introduce spacer, as spacer can provide flexibility to the ligand to interact with the target more effectively. This is based on the previous study that we studied. So we try to introduce spacer, which is beta-mercaptoethanol. As you can see from the figure 11, when we this is the mechanism, the theoretical mechanism. When we introduce BME, the tripeptide might be in the correct orientation to capture our target effectively. However, as you can see in figure 12, we try to compare between mixing method and also the replacement method, where in the mixing we mix BME with the tripeptide together. And for replacement, we introduce BME first and then tripeptide. So as you can see here, ratio 0.10 means 0 BME and 10 tripeptide. So we can see that the pattern is, the trend is, the higher concentration of BME, the higher the concentration of BME, get the lowest sensing signal, similar to replacement method. So we conclude from here that our tripeptide alone are enough to capture metal ion. So without BME, without spacer, our tripeptide can work alone to have the correct orientation for capturing mercury ion. So the next part is we compare before and after optimization. We can see that after optimization, our sensing signal increase. Apart from that, we can see that our heteroligand system, which is DCH HCD, show higher absorbance ratio compared to the monoligand HCD and also DCH. As you can see here that DCH only have around 0.7 absorbance ratio, HCD around 0.9, DCH HCD around 1.0 above. So we conclude here that using two different heteroligand will give this higher sensing signal, which can help in detecting lower concentration of mercury, maybe up to 25 ppb or 10 ppb. So the next part is we do some study for DCH, HCD, AMP, where we try to see the selectivity, and you can see here that DCH, HCD are selective toward mercury over 9 others metal ion, and this is the particle size, PDI, and zeta potential. You can see here that the particle size increase and also the PDI value increase, which indicate that aggregation occur. And you can see here that in heteroligand DCH-HCD, our particle size increase and also PDI increase higher compared to monoligand DCH and HCD. And also for zeta potential, DCH-HCD heteroligand has give the negative 70, which means getting increased. This is because the heteroligand disease HCD capture more positively charged mercury compared to monoligand disease and HCD. So we also done transmission electron microscopy to visualize the our gold nanoparticle. So you can see before addition, the nanoparticle are in a loose cluster. However, after the addition, the nanoparticle aggregate and overlap, forming the solid cluster. So we also done validation of heteroligand system, where we conjugate the different size of gold 20 and 40 to observe interaction. So based on the theoretical illustration aggregation, we there will be like a nanoflower structure occur. This is our image that we capture from our transmission electroscopy analysis. Transmission electron microscope analysis. So you can see here that there is interaction between DCH and HCD, as HCD be conjugated onto 40 and DCH on 20. So you can see for the zeta potential, this increase to -8, which means this pair can capture more mercury ion compared to when we use same gold particle. So the conclusion of my study is, in this study we developed a system which utilized two novel type of ligand, which is designed like tripeptide, DCH and HCD, for detecting mercury ion. So from the finding, combination of these tripeptide selectively capture metal ion, hence proving the ability to be utilized as an effective capturing system for a small molecule. And besides, this system have been proven to be more effective compared to monoligand system. Thank you for all your attention.